Okay, here's a question about emission and absorption spectra. As ever, have a go, and when you're ready to seize an attempt at an explanation anyway, please press play. Okay, I think if anyone's expecting a huge bit of work here, you're going to be disappointed. I think this question is quite a simple one with a bit of common sense. Okay, firstly, I think it's worthwhile reminding ourselves what we mean by absorption and emission spectra. Okay, I think that's probably more sort of important here. Our absorption spectra, okay, that's the ones, let me get this right, on the top. Okay, the absorption spectra are majority color with bits of black, and the emission ones are the opposite, the inverse if you like. So where you have dark points in the absorption, you have light in the emission. Now, where we might use this, if we're looking at a star, for example, we'd be trying to determine which elements are in that star. Well, we would look at the emission spectra, and then we would decide, okay, what is in there purely from its kind of fingerprint. And it's kind of a hard process to do, but you can eventually tell which elements are in there. Okay, so they absolutely provide information on the chemical composition of substances, and if we're ruling things out, that then gets rid of C. They provide no evidence for mass energy equivalence. Okay, I don't really know how to answer that other than to say that it's not the case. Okay, mass energy equivalence is a much deeper topic. Well, I mean, okay, that's probably not fair to say. It's a different type of topic. I mean, the mass energy equivalence that we tend to deal with in IB would be the change in mass when we separate out nuclei into their constituent parts. And absolutely, they arise from transitioning electrons between energy levels. They are really the evidence for the idea of electron levels, the idea that we have fixed orbits where the electron can occupy and transition and therefore either jump up or jump down, which is why the answer here is B.